Welcome to This Explainer. Okay, today we're taking a really grand, awe-inspiring journey. We're going to bridge the massive gap between the colossal forces of astrophysics and, well, the everyday technology bolted to the roof of your house. We're diving into the mechanics of solar systems. And yeah, both the celestial one we literally live in and the electrical one you might be using to power your life right now. I know, you're probably wondering, what does a 4.6 billion-year-old exploding star have to do with your refrigerator? It kind of sounds like the setup to a weird joke, doesn't it? But I promise you, there is a direct, incredibly fascinating line between the violent birth of our universe and the quiet hum of the appliances sitting in your kitchen today. Okay, let's dive into this roadmap. We'll start with the birth of a star, explore gravity and the cosmic dance, and then zoom right down to Earth for harnessing the sun, inverters, translating the power, and finally, storing energy for the night. Section 1. The birth of a star. So we're traveling 4.6 billion years into the past, way before Earth even existed. Our story actually starts with a primal supernova, this massive exploding star, sometimes called Kotli-Kui. This explosion sent out a shockwave that triggered the collapse of a giant molecular cloud. And as this cloud collapsed, it started spinning faster and faster, flattening out into a protoplanetary disk. Millions of years later, inside this swirling disk, tiny little dust grains started bumping into each other. This is a phase called runaway accretion, which formed larger rocks known as planetesimals. Eventually, things slowed down into what's called oligarchic growth. This is where those rocks smash together to form planetary embryos, literally the rocky foundation of our very own Earth. Now, what were those early embryos actually made of? Well, that massive collapsing cloud was 98% hydrogen and helium, the absolute lightest elements. But that remaining 2%? That is where things get really interesting for us. It contained heavier elements, things like carbon, oxygen, and iron. And these elements didn't just magically appear, right? They were forged deep in the cores of much older stars and then blasted out into space when they went supernova. So think about this. The building blocks of our rocky planets, our modern solar panels, and eventually us, we were literally recycled from older exploded stars. Crazy, right? Section 2. Gravity and the cosmic dance. Now that we've got all these raw materials spinning around a newly ignited, very young sun, we have to look at the incredible physics that keeps everything organized. Like, why aren't they just crashing into each other or flying off into deep space? So the crucial point is 99.8%. That is the percentage of mass in our entire celestial solar system that belongs strictly to the sun. Seriously, wrap your head around that. Jupiter, Saturn, Earth, all the asteroids combined, they all fit into that tiny remaining 0.2%. Because the sun is just so unbelievably massive, it acts as this ultimate anchor, using its gravity to pull literally everything else toward its center. But wait, if the sun is pulling everything inward, why don't the planets just fall into the sun and, burn up? Well, it's basically a 4.6 billion year long tug of war. On one side, you have gravity relentlessly pulling mass inward toward the sun. On the exact opposite side, you have inertia. The planets are actually still carrying the forward momentum from that early spinning disk and that initial explosion. And that momentum makes them want to travel in a perfectly straight line away from the sun. And when you combine those two fiercely competing forces, the inward pull of gravity and the forward push of inertia, you get centripetal force. This specific resulting force is exactly what pushes our planets into that elegant elliptical orbit. It's like an invisible, perfectly balanced cosmic string keeping the planets securely locked in their circular paths, instead of just flowing off into the absolute void of space. Section 3. Harnessing the sun. All right, let's zoom all the way in now. We are leaving the massive macro scale of celestial mechanics and dropping right down onto, say, a residential rooftop. And this brilliantly illustrates a really cool parallel. Just as the celestial solar system uses gravity to anchor planets and moons around a central energy source, we've gone ahead and built our own localized home solar systems. Except instead of planets and gravity, our localized systems use panels, inverters, and batteries to capture and manage that exact same cosmic energy, just on a much more micro scale. So how do we actually capture it? Well, it happens in 3 pretty elegant steps. Step 1, sunlight, which, by the way, takes about 8 minutes to travel all the way from the sun to your roof. Hits the solar panel's silicon cells. Step 2, This physical interaction triggers what's called the photovoltaic effect, which generates free electrons inside the silicon. And step 3, these electrons are forced to flow through a circuit, and this creates raw electrical power, known as direct current or DC electricity. Guys, that is literally ancient starlight being actively transformed into electricity on top of your house. But capturing this energy efficiently doesn't just happen anywhere. It requires some really specific conditions. Obviously, you need optimal sunlight exposure without trees casting shadows all over the place, and the correct panel angle, usually ideally facing south if you're in the northern hemisphere. But take a look at that third point. The ideal operating temperature is around 77 degrees Fahrenheit or 25 degrees Celsius. This is a hugely surprising fact for a lot of people. Panels actually perform best in cooler conditions, not in extreme blazing heat. High temperatures can actually disrupt the silicon's efficiency and cause a pretty big drop in power. Section 4. Inverters. Translating the power. Okay, so we've got all this raw power flowing off the roof, but you can't just take your television and plug it straight into a solar panel. The big issue here is a mismatch in the type of electricity. See, solar panels generate direct current, or DC, and batteries, they store energy in DC too. But standard home appliances, the fans, your computer, that refrigerator we kept mentioning at the start, they absolutely require alternating current, or AC. If we don't convert the current, all that amazing solar energy is completely useless to the modern home. Now, what's really interesting about this slide is the solution. Enter the inverter. This little box is truly the heart of the home solar system. It basically acts as an electrical translator. It takes that raw, completely unusable DC electricity and rapidly converts it into the safe, usable AC electricity that then seamlessly flows right into your switchboard. This one single device is the magic key that allows your standard everyday air conditioner to run directly on ancient starlight. Section 5. Storing energy for the night. Of course, as we know, the Earth rotates and the sun goes down, so we have to ensure that all this power we captured during the day stays available when our side of the planet turns away from the sun. To solve the nighttime problem, a hybrid solar system essentially performs a really seamless 4-step juggling act. First, the panels generate that DC power. Second, the inverter converts exactly what you need for immediate home use. But here's the kicker. During peak sunlight, you're usually generating way more than you're actually using. That excess DC power doesn't just go to waste. Instead, step 3, it gets routed straight into charging your solar batteries. Then finally, step 4, when the sun sets, the system flips and the batteries supply all that stored power right back to the house. But hold on, you can't just shove electricity into a battery indiscriminately. That's a recipe for disaster. That's where this next crucial component comes in, the charge controller. You can think of it as the system's traffic cop. It meticulously regulates the energy flowing into the batteries, strictly preventing overcharging or deep discharging. By carefully managing the entire system's balance and safety, the charge controller protects what is typically a very expensive battery investment and makes sure it lasts for years. Let's move to and see how this builds true energy independence. By adding battery storage, you secure your home in 3 exact scenarios. First, obviously, powering the home at night when there's zero sun. Second, supporting the house on really overcast days. Did you know that heavy cloud cover can drop panel efficiency down to just 10 to 25%? A battery perfectly bridges that gap. And third, it provides totally vital protection and backup power during local grid outages. Which actually brings us to the end of our explainer today. But I want to leave us with one final provocative thought. We know from our celestial timeline that in roughly 5 billion years, the sun is going to run out of hydrogen, expand into a massive red giant, and drastically alter our entire solar system. Now, long before that happens, how will our localized, earthbound solar systems evolve? How is the technology sitting on our roofs going to adapt as we continue to find entirely new ways to capture the cosmic dance of the stars to keep our lights on? I'll leave you to ponder that one. Thank you so much for joining me on this absolute journey from supernova to switchboard.